Alright, so to wrap up chapter 3, we're going to talk about the kinetic molecular theory of gases and how real gases actually differ from ideal gases. Kinetic molecular theories exist for solids and liquids as well, but since gas particles move so much faster, the kinetic molecular theory for gases is just the most interesting of the three, so that's the one we'll discuss. The kinetic molecular theory is composed of several points, and we'll just go through those here quickly. The first point is that a gas is composed of molecules, particles, atoms, that are separated from each other by distances that are far greater than their own dimension. That means that we know atoms and molecules are very tiny. The distance between them is very large. Molecules can be considered to be point particles. That is that they have mass, but they take up hardly any volume, negligible volume. So most of the space that's being occupied by a container full of gas is vacuum, and the particles of gas actually make up just a small volume within that container. The second point is that gas molecules are always in motion. They move in random directions. They collide with other gas molecules all the time, and that the equations are perfectly elastic. For those of you that hadn't taken physics yet, an elastic collision just means that they hit each other and they don't lose any energy in that collision. All the energy is maintained. Gas molecules exert neither attractive nor repulsive forces on one another. This just means that they aren't drawn toward each other. They don't repel one another. They are don't really care that other gas molecules are around. And then the last point, the average kinetic energy of the molecules is proportional to the average temperature of the gas. That temperature has to be in Kelvin. So the higher the temperature, the faster those atoms, those molecules are moving. Two gases at the same temperature will have the same average kinetic energy. Now there is a relationship between the kinetic energy and the speed. If you have had physics, maybe you remember this. The kinetic energy is equal to 1/2 mu squared. Now this kinetic energy has a bar over it, right? And that's just for average. The speed squared just has a bar over it. Again, that's just for average. U, remember, is speed. Speed has units of meters per second. M is our mass. And our mass here is going to be in kilograms. You can tell from this equation that the higher the mass, the lower the speed. So for the same kinetic energy, that is the same temperature, the larger molecules will be moving slower than heavier molecules. Let's take a look at a graph and see how this plays out. So here we see that for nitrogen, so this is the same molecule. For nitrogen at different temperatures, at 100, 300, and 700 Kelvin, we see different speed distributions. The thing to note here is that the area under this curve should be the same for all three temperatures. We're not changing the number of moles of nitrogen gas, we're just changing the temperature of the gas. And so here at 100 Kelvin, that most probable temperature, right, that it's not quite the average, because maybe you'll notice out here that we have sort of this high energy tail that don't match, the wings don't match on that curve. And so the average is actually here somewhere. I'll just mark that. We call this the most probable speed. Because it's the highest, the most number of molecules are there. And so that most probable speed is relatively low versus at 300 Kelvin, that speed increases, and at 700 Kelvin, that speed increases even more. Okay? So let's take a look at one gas at three different temperatures, but how about three gases all at the same temperature? If we look, now we're stuck at one temperature, 300 Kelvin, but we have gases with different molar masses. We have a 71, a 28, and a 4. Notice that the heavier the gas, chlorine, has the lowest most probable speed. Nitrogen has the next lowest, most probable speed, and helium, by far the lightest of these three, has the highest, most probable speed. Now, the most probable speed is a speed that we do use a lot, but it turns out that really more often than that, what a lot of people pay attention to, what a lot of people use, is something called the root mean square speed. The root mean square. This is abbreviated RMS. And so the RMS speed is equal to the square root of 3RT divided by the molar mass. Again, I'm going to use the double M's as molar mass. Our textbook uses a large script M. This is where it gets a bit confusing. We need speed to be, I'm going to change ink colors, we need speed to be in units of meters per second. R is liter atmospheres per mole Kelvin. Even if temperature's in Kelvin, we don't have anything to cancel out liters or atmospheres, and we have no way of getting meters or seconds. And so we have to change the value of R that we're using. And so for us, just for this equation, R is 8.314 joules per mole Kelvin. Okay? Now that is the same gas constant. It's just in different units. If you went through and you figured out the conversion between liter atmospheres and joules, you would be able to convert our 0.0821 liter atmosphere per mole Kelvin into 8.314 joules per mole Kelvin. Joules are kilograms meters squared per second squared. And so as long as our molar mass is in kilograms per mole, what's going to happen is that kilogram here will cancel out, and we'll be left with meters squared per second squared. We take the square root, and it works itself out. Let's do an example, and I'll show you what I mean. Calculate the root mean square speeds of helium atoms and nitrogen molecules in meters per second at 25 degrees C. Well, first let me jot down our equation. URMS is equal to the square root of 3RT over molar mass. So I need a few things. First, I need this temperature, not in Celsius, but in Kelvin, 298 Kelvin. And I need the molar masses of both helium atoms and nitrogen molecules. Not an atom of nitrogen, but nitrogen molecules. For those diatomics, be sure you watch out for that. And so the molar mass of helium from the periodic table, 4.01 grams per mole. But I don't need this in grams per mole. I need this in kilograms per mole to cancel out my joules. And so I need to convert grams to kilogram, and 1 kilogram is 1,000 grams, and I'm left with 0.00401 kilograms per mole for helium. For nitrogen, it's 28.02 grams per mole. I'm just going to do that conversion, 0.02802 kilograms per mole. Okay. Now that we have those things, let's plug that into our equation. So U for helium is the square root of 3 times R. Remember, we're changing things up. 8.314 joules per mole Kelvin times 298 Kelvin divided by the molar mass. Helium was 0.00401 kilograms per mole. Okay. So let's do this. 3 times 298 times 8.314 divided by 0.00401. That's a big number. We take the square root, and we get the speed for helium is 1,360 meters per second. Pretty fast. Let's do the same for nitrogen. Nitrogen's heavier. Just as a check, do you think it should be faster or slower? Let's find out. 3 times 8.314 joules per mole Kelvin times 298 Kelvin divided by 0.02802 kilograms per mole. Plug that into the calculator. Take the square root. For nitrogen, we get 515 meters per second. Nitrogen is a heavier molecule. We end up with a slower average speed. What happens when gases don't behave ideally? Real gases sometimes deviate from ideal behavior, and there's 2 main causes. The first cause is that there are attractions between gas particles. Remember, that was part of our kinetic molecular theory, that we ignore those interactions, but there could be attractions between gas particles. We call these intermolecular forces, and we'll get to them at the very end of this semester, hopefully. So you may have heard that term before, intermolecular forces. It's part of chapter 11. So attractions between gas particles. What this does is it reduces the pressure in our container. And it does that by, when particles go to strike the wall of the container, they strike with a little bit less force because they're being pulled by other molecules that are in that same container, which causes the pressure to be slightly lower. The other component, the other thing that we ignore in the kinetic molecular theory, is that we said that gas particles were point particles. They had negligible volume. So sometimes we have to pay attention to that molar volume, the actual volume that gas particles take up. This is really important when the pressure is large and the volume of our container is small, because the volume of the container can't go to 0 because our gas particles are in there. And as our container gets smaller and smaller, sort of the fraction of that container that is actually the physical volume occupied by those atoms, those molecules, gets to be a larger and larger percentage. And so what the molar volume does is it reduces the volume that's available for all the other atoms, the other particles, to move around in. Because no 2 particles can overlap, if we're in a small enough space where I've got gas particles, they can't occupy the same volume, and so the total volume of my container is whatever the volume is minus the volume of all the other gas particles. And so this lowers the volume. This ratio here, PV over RT, if you know your ideal gas law, you'll know that this is equal to N. And for an ideal gas, this is exactly 1 at all pressures. It turns out that for a real gas, it has some curvature to it. And it can either be less than 1 or greater than 1, and these are caused by 2 different types of deviations. For the first, these attractive forces, that's all in here, right? These are the attractions between gas particles. And up here above 1, that's all due to the molar volume. Sometimes we call those repulsive forces because those gas particles are repelled from being in a particular volume by other gas particles that are already taking up that space. And so we call these repulsive forces. Okay. Notice that the pressure here, these pressures are very high, 1,000 atmospheres, and so these deviations from ideal behavior really happen only at very extreme situations. If we were talking about atmospheric pressure, we're talking about 1 to 2 atmospheres, almost all gases behave fairly ideally. It's just as we increase pressure that they start to behave non-ideally, like real gases. There is an equation to help us explain the behavior of real gases. That's called the van der Waals equation. The van der Waals equation takes into account both those attractive forces and the molar volume of a gas. And so if we look here, this first term, the pressure plus this AN squared over V squared piece, this is the corrected pressure. I like to think of this as the ideal pressure. Right? And so the real pressure plus this little bit is equal to the ideal pressure. Remember that those attractive forces make the pressure a little bit smaller than what it would be according to the ideal gas law. This second term, the corrected volume, again, I think of as the ideal volume, because it's the amount of volume that those particles have to move around freely if the actual particles didn't take up any volume, if they were in fact point particles. And so here, this volume is the volume of our container, and this N times B bit is the volume of the gas particles. The nRT on the other side of the equation doesn't change, and so we have this new version of pressure and this new version of volume equals nRT. Now if you'll notice, we have N and V, that's the number of moles and the volume. Here we have N as well, again, number of moles. But we have two new terms, and that's A and B. A and B are experimental values. They're constants for each individual gas. And so if you look over here at the table, right, we have these experimentally determined constants for different gases. The problem that we're going to look at next is ammonia, which is here behind my webcam. And so for ammonia, A is equal to 4.17 and B is equal to 0.0371. The units on A are atmospheres, liters squared per mole squared, and the units on B are liters per mole, that molar volume. So let's do a problem looking at those two, 4.17 and 0.37. All right? So if we have 3.5 moles of ammonia in 5.2 liters at 47 degrees C, let's calculate this pressure using both the ideal gas law equation and the van der Waals equation. And so if we do the ideal gas equation, P equals nRT over V, that's 3.5 moles times 0.0821 liter atmospheres per mole Kelvin. 47 degrees C plus 273, that's 320 Kelvin. Divide all this by 5.2 liters. And for the ideal gas law, we get a pressure of 17.7 atmospheres. Okay. Now that's not a super high pressure like we saw on the graph, 800 or 1,000 atmospheres, but it's certainly much higher pressure than we experience on a day-to-day basis here in the lab or something like that. Now, using the van der Waals equation, P plus A, 4.17 atmospheres liters squared per mole squared, times the number of moles squared, 3.50 moles squared, divided by the volume squared, 5.20 liters squared, times the volume, 5.20, minus, in the number of moles, 3.50 times B, 0.0371 liters per mole, equals nRT, 3.5 moles, 0.0821 liter atmospheres per mole Kelvin, times 320 Kelvin. This looks like a lot, but really it's just algebra. If we do everything on the right, 3.5 times R times 320, we get 91.95. Now, our moles cancel and our Kelvin cancels, and so this is liter atmospheres. All this V doesn't have any variable in it, so we can do that. And the volume doesn't change very much. We end up with 5.07 liters. And now we keep our variable P and we add on this little bit. Don't forget to square the number of moles and the volume. So 4.17 times 3.5 squared divided by 5.2 squared is 1.89 atmospheres. So I need to get P by itself. I'm going to divide both sides by the volume. So I end up with P plus 1.89 atmospheres is equal to 18.1 atmospheres. Subtract 1.89 from each side, and I get P is equal to 16.2 atmospheres. So the real pressure is a little bit smaller than the ideal pressure. If we think about our graph, that's less than, the pressure is less than what we imagined. And so that value, that ratio is less than 1. And so in this area, those attractive forces are stronger than those repulsive forces. Okay? That's the end of Chapter 5. Remember that we will have office hours via Zoom Monday at 2 o'clock Eastern Time. I hope you can make it. If not, please let me know and we'll try to arrange something differently. This is the end of Chapter 5 material. You'll have a quiz on this material April 10th. Okay? Take care.